contribution. Okay. So this system, this is 132 avoiding patterns. Oh, no numbers. This is what we did. These are loops. Okay. I also had for 5. I also have this this is 1, 2, 3 avoidance. Sorry, this is 1, 2, 3 avoidance. This is 1, and these also have loops. This is 132 avoiding patterns. What we call graph theoretic approach. So we identify this as networks. These are efficient networks. Okay. So this we did in around 2007. So this is 21st century contribution we did on networks. So that's it about the history. I think we can now go to the review. Okay. Now, I have problem with markers. They seem to be not too good. Review. We are going to review our knowledge on mathematical structures. Okay. And under this, I think we would like to know what are groups, are rings. Okay. Are related, like fields, domains, and so on and so forth. Okay. And by groups, we are going to go to abelian groups. Okay. Finite groups. Okay. Why do we require this? Because we are going to come across how to transform these structures, okay? As we, for example, in category theory, we're going to be dealing with these structures as categories now, okay? So, what is group?
Good morning.
Good morning. You're welcome. You're welcome. Well, fine. Yes. We are going to categorize them into finite and infinite. Okay. The finite groups are those with finite number of elements. The infinite groups are those with infinite number of elements, like the Z5. This has 5 elements. This has infinite number of elements. Good. Now, we also want abelian groups. What are abelian groups? G abelian implies what? For any x1, x2 in G, x1, x2, same as x2, x1, okay? So this is another name for this is commutative. To say that any two elements are commutative in G. So G is abelian now, okay? If you generalize for all the elements of G, then G becomes an abelian group. What we also need to know about this is the homomorphism, for example, of groups.